National Data Archive on Child Abuse and Neglect.
All right, hello everyone. Welcome to our 2026 NDACAN Summer Training Series. My name is Lisa Lindsay. I'm the Graduate Research Associate here at NDACAN. Before I kick off our time together, I just want to give a couple of housekeeping items. We're recording this session so that we can post the recording, the transcripts, the slides, and any related materials on our website several weeks after each presentation. And I'll announce their availability on the Child Maltreatment Research L or CMRL listserv, and I'll put the information on how to join that listserv in the chat. Throughout the session, we have a Q&A box at the bottom right of the screen. So as we're going through, feel free to leave your questions in that Q&A box. And at the end of the presentation, we'll go through each question as they come in. Next slide. Great. So welcome again to the NDACAN Summer Training Series. NDACAN stands for the National Data Archive on Child Abuse and Neglect, and it's housed at Duke University, Cornell University, UC San Francisco, and Mathematica. Next slide. NDACAN does 2 learning offerings every year. We have our monthly office hour series during the academic year, and in the summertime, we have a summer training series. The theme of this year, 2026 Summer Training Series, is laying the groundwork, foundational skills for using administrative data in child welfare research. This series is designed to strengthen the foundational skills necessary to conduct high-quality, impactful research with administrative data. And we're intending this to be useful both for folks who are new to this area and are seeking to strengthen existing skill sets. So throughout these summer presentations, we're aiming for each session to be a useful and thorough starting point for conducting research on child welfare using administrative data. Next slide. This is just a preview of our schedule for the 2026 Summer Training Series. We'll be meeting every Wednesday at 12 Eastern for an hour, and these are the topics we'll cover. Last week, we kicked things off with an overview of NDACAN administrative data sets. The materials from that session will be available soon, and we'll announce that on the listserv. Today's session will cover data cleaning and management, and the following sessions will be over linking NCANs and AFCARs, handling missing data, and we'll end with a presentation on data presentation and visualization. Next slide. So again, today's session is going to start with some general advice and overview on data cleaning and management, and then a brief demonstration in R, followed by a question and answer session. Next slide. So now I'll pass it over to Alex to lead the rest of today's discussion. Thanks.
Thanks, Lisa. My name's Alex Roehrkasse. I'm a research associate at the archive and an assistant professor of sociology and criminology at Butler University. I used to be a postdoctoral associate at the archive, so I've been doing work with the archive for 6 or 7 years now, and I really enjoy this part of my work. Giving these presentations is also one of my favorite things to do. So today we're talking about data cleaning and management. This is a broad topic and involves a lot of core skills, foundational skills that we're going to be trying to build this summer. So I want to acknowledge upfront that we're not going to be able to cover everything. The presentation today is going to be a little more focused on some key skills and key strategies that I have found useful both as a data user and a data consultant in working with archive data, particularly our administrative data sets. Some of the materials and topics that I cover in my slide deck today, we will do demonstrations of next week in the session on linking data, where those skills are especially relevant to data linking. Also, I want to note that some of the material today may feel a little bit slow to some of you. Some of it may feel quite fast to others. That's partly because we're trying to pitch this presentation to an audience with multiple and diverse skill sets. So I just want to remind you that both the slides and the code for today's presentation will be available on our website. So if you feel yourself falling behind or getting a little bit lost, rest assured you can circle back to the materials that support today's presentation and study them a little more carefully in a few weeks. As always, we're available to help, so don't hesitate if you have questions today. Please, as Elisa said, drop them in the chat. If questions strike you 2 hours, 2 days, or 2 years from now, don't hesitate to shoot us an email. we're always happy to talk. Okay, with that, let's get started. I want to start today's presentation with some general advice. First, use what's available to you. You may have lots of support at your institution or your workplace. You may have very little. Whatever resources you have outside of the archive, I want you to know that the archive is really a rich resource for you. Particularly our website has a number of different helpful resources, including past versions of this very training, where you can go to access key information that can support your research using archive data. So if you haven't explored our website, I strongly encourage you to explore it. Second, as I've kind of already said, please don't hesitate to ask for help. NDACAN staff and research associates like myself are really here to support all aspects of research using data that the archive distributes. There's real value in struggling yourself with critical research questions and challenges. But if you find yourself beating your head against the wall for a week or 2 weeks, please shoot us an email. We're always happy to talk about challenges and strategies for solving them. Lastly, at risk of stating the obvious, artificial intelligence is becoming an increasingly powerful tool that has potential to support research involving archive data. I myself am exploring ways that AI can support my own research, but I want to be really clear. It's very important that you develop the skills, the experience, and the discernment so that AI can be a complement to your research rather than substitute critical functions in the research process. I like to think of data management as crisis management. We're trying to optimize a lot of things, but we're also trying to avoid disasters. What are the kinds of disasters that can arise, and what are the kinds of things we can do to manage that risk? One thing is that you're going to make mistakes. Everyone makes mistakes, no matter how skillful or experienced you are. Some of those mistakes will be small, some of them will be big. One of the best things you can do to protect against mistakes is to save and back up your work often. For example, when I'm coding, I save a new program file every single day that I'm doing meaningful work on that code. What that means is that if I realize a day later or 2 days later, or sometimes even a year later, that I made a mistake, I made a bad decision, I can always go back and find my code before I made that bad decision. I can't tell you how often it's been helpful to have archived code that's clearly dated and organized in a clear way. Also, you won't remember. You think you will, but you won't, whether it's minutes later or hours later or years later. Some research projects take a very long time. Even though it feels like when you're making a critical decision, you're very sure you'll remember making that decision, I promise you, you won't remember all of those decisions. This is another reason why saving and backing things up is important. As I'll explain when we get into our demonstration in R, it's also a good reason never to code from the console. As you'll see, we can tell statistical programs like R or Stata to do things ad hoc. We can type in commands and have them execute them on the fly. I strongly recommend against doing this, ever. You'll always instead want to write a program file, which is a file you save on your computer, and only ever to execute functions or ask a statistical program to execute a function that you've written down. This way, you'll always know what you told your computer to do. You'll also see in the demonstration that I like to annotate my code liberally. So when I'm coding, I'm also writing notes to myself in that code that explains what I'm doing and why I'm doing it. Lastly, I like to keep a research journal for every research project that I'm working on. I make an entry into it at least once a day, and it's a place where I write down decisions I've made, questions I have, challenges that arise, to-do lists. Sometimes these research journals have gotten 40, 50, 80, 100 pages long. And again, I can't tell you how often it's been helpful to go back to those research journals to understand critical decisions I've made. Lastly, insofar as we're participating in a scientific community, a cumulative process of discovery, it's important that other people can understand what we've done and why we've done it. Other people can't read your mind now or in the future. This is another good reason to annotate code liberally so that When you publish a replication package, people can't just run it, they can understand your code. Keeping a research journal is also important here. I get a number of questions from other scholars about my research, and I frequently consult my research journals so that I can have dialogue with other researchers about my research. Lastly, I want to suggest that file organization and workflow is a pretty critical part of doing effective research using large administrative data sets, particularly data sets that include sensitive information with restrictions. I like to have two basic folders that I use whenever I'm doing a research project involving restricted administrative data. I have a project folder that's usually on my local machine, but that project folder is backed up regularly to a cloud server. In that project folder, I have a programs folder where I'm saving each of those daily program files. And then I have a separate subfolder that includes all of my output, figures I make or tables I make, as long as those tables only include de-identified data. That is to say, summary statistics, any information that's not going to identify any of the respondents in my data. I then have a separate data folder. This is where I keep my raw data, the files that are distributed directly by the archive, and also any derived data, any data that I've manipulated, but which still includes microdata or data that could be identified. Now, it's very important that this folder, wherever you place it, follows the stipulations of NDACAN data use agreements. At present, most data use agreements allow either for a FedRAMP authorized cloud server or an encrypted external drive. Whichever works best for you is totally fine, but it's essential that you make sure that any identifiable data resides in one of those secure places. You'll see this workflow, this file organization demonstrated in the second half of the presentation today. Okay, so this brings us to the actual data cleaning and management. The very first step in this process is trying to understand your data, trying to get a glimpse of it, trying to examine it. This involves asking questions like, what's the basic structure of your data? What are the columns in your data set? What are the rows? Most NDACAN administrative data sets are really, really large. They're much too big to just open in Excel. And so we often need to think creatively about what viewpoint onto our data do we need in order to best understand it. How can we pull out certain columns or filter out certain rows or summarize certain values in order to understand the structure of our data, the contents of our data set? Once we've examined our data and have some sense of what it actually looks like, what it actually contains, then we usually set about trying to clean it up. We do our best to make sure that the data we distribute are pretty clean, but there's always some issues. And besides, whatever clean data means to you depends a little bit on what your research goals are. Cleaning your data requires you to ask questions like, how are variables formatted? There's different kinds of variables depending on the kinds of values that they contain. String or character variables, for example, usually contain alphanumeric text. Numeric variables or integer variables include only numbers. Factor variables are categorical variables that have some ordering structure to them. There's many other kinds of variables or formats of variable, and it's important to understand how your variables are formatted. Second, how are values coded? This is what we most often use a code book for. We refer to the code book to tell us how any given variable is encoded. But it's important, and as I'll demonstrate later, the codes in the actual data sets that we distribute don't always correspond to the way they're described in the code book. For this reason, it's essential that you always verify the encoding of every variable that you're interested in using in your analysis. Lastly, and arguably most importantly, what formatting or encoding do you want? What formatting or encoding would best capture the relevant information that you need to do your analysis? Obviously, this is limited by the data itself, but it also depends on your analytic goals. Another very basic thing that some users overlook, but which is really pretty critical, to the early stages of your research process is to think carefully about your unit of analysis. Your unit of analysis will depend on your research question, but even different research questions can admit different units of analysis. What's important to understand is that, sort of by default, all of the administrative data sets that we distribute have more or less a default unit of analysis that corresponds to whatever a row represents in that data set. So for example, if you were to download the NDACAN's child file, each row in those files would correspond to a child report. NDACAN's tracks reports of investigated child maltreatment. And so each row corresponds to a distinct child who experienced a distinct report. What this means is that any given child can have multiple child reports if they received multiple reports. And each report can have multiple child reports insofar as multiple children were involved in a single report. For AFGARs, the layout is somewhat different. The unit of analysis is the child year. So in any AFGAR's foster care file, if a child passes through the foster care system in that year, they'll have exactly one row. So the unit of analysis in AFGARs is the child year. In NIDED, which is a repeated observation study, the unit of analysis is the child wave. Your research question may correspond to these unit of analyses, but it very likely doesn't. And so in this case, you'll need to reshape your data, tidy your data, some way or another modify your data to capture your unit of analysis. Briefly, by way of example, 2 research questions. First, how many children experienced a maltreatment investigation in each US state annually? In order to answer this question, we would have to take NDACAN's data, but then drop records from those files from subsequent reports experienced by children within the same year, and then count up all the remaining records by each state and year. A second research question, how many maltreatment investigations occurred in each half month? Here in NDACAN's, we would drop records from additional children covered in each investigation, and then count up the records of each distinct investigation grouped by each half month. As you can see, the research question dictates the unit of analysis, which in turn dictates how we'll reshape, how we'll tidy our data. A last, very basic but very essential question is to clarify your sampling frame. Different research questions recommend different temporal sampling frames. For example, maybe I want to study all children in fiscal year 2018, or in calendar year 2010, or maybe I want to follow the 2012 birth cohort through age 6. Using administrative data, it's very easy to confuse the timing of an event's occurrence with the timing of an event's reporting. Let me give an example. A maltreatment investigation included in the 2019 NDACAN's child file may actually have occurred in the 2018 or 2020 fiscal years. Conversely, a child maltreatment investigation that actually occurred in fiscal year 2019 might show up in the 2020 NDACAN's child file. For this reason, careful combination and tidying of multi-year data is often needed in order to sample validly. Let me give a brief illustration of this. Here you see just a 1% sample of the 2019 and 2020 NDACAN's child files. This bar graph shows the number of records on the vertical axis, and each half month is plotted on the horizontal axis. Data from the 2019 child file is in blue, and data from the 2020 child file is in red. Let's say we wanted to know the number of maltreatment investigations that occurred in the fiscal year 2019. If we only used data from the 2019 child file, it would seem that records started to taper off toward the end of the federal fiscal year. But this would be an artifact of the timing of reporting in the NDACAN system, because as you see from the red bars, a certain number of reports that actually occurred in the 2019 federal fiscal year only made it into the 2020 child file. And those delayed reports were concentrated at the end of the 2019 federal fiscal year. Once we've cleaned our data, once we've thought carefully about unit of analysis and sample, ideally we'll arrive at what we like to call tidy data. What is tidy data? A tidy data set is one in which each observation should have its own row. Basically, whatever your unit of analysis is, each distinct observation of that unit should have its own row. Each variable should have its own column, and each value of a variable should have its own cell. Whenever one of these things isn't the case, it's okay, don't freak out. But it usually does mean that we need to summarize or pivot or do some other manipulation to our data to arrive at tidy data. So very briefly, I'm going to illustrate both summarizing and pivoting data, which are two of the most common strategies we use in order to get tidy data. First, summarizing. What is summarizing? Summarizing is what in other languages we call collapsing or but in R, summarizing means essentially taking multiple rows of data, reducing them to a smaller number of rows, and in doing so, creating some new variable that summarizes information in the original raw data. Let me walk through an example briefly. Here is a sort of toy example of some NDACAN's data. In the first column is the fiscal year. We have data from 2021 and 2022. In the second column is a unique child identifier. So each child gets a unique and consistent value of this variable. Here we have two children, one from Alabama, who shows up twice here, and one from Kentucky. In the third column, we have an actual variable from NDACAN's report disposition. This is the disposition that the investigation gets after being investigated. 1 for this variable means that the report was substantiated. 5 means that the investigation did not substantiate the allegation of abuse or neglect. In this raw data, the unit of analysis, as it is in the distributed NDACAN's child files, is the child report. So each row corresponds to a unique combination of the child identifier and the report, which means that children can have multiple child reports in a given year. Let's say, though, we want our unit of analysis to be the child year rather than the child report. In this case, what we need to do is collapse or summarize multiple observations of a distinct child in a single year. So we tell R, let's summarize our data, collapsing it essentially by year and child ID, and in doing so, generate a new variable that counts the number of substantiated investigations that the child experienced in that year. For the Alabama child in 2021, this is 2 because they experienced 2 substantiated investigations. For the Kentucky child in the same year, it's 1 because they only experienced 1 report. Notice that for the Alabama child in 2022, same thing, but for the Kentucky child in 2022, note that even though they had 2 reports, only 1 of them was substantiated, and so this is the value of our variable for that child in that year. This is an example of using summarizing as tidying, where if we need our data to correspond to a new or different unit of analysis, such as the child year, we can summarize or collapse our data to create a new unit of analysis corresponding to each row. What about pivoting? Pivoting is another way of sometimes reshaping our data to arrive at tidy data. Here on the left, you'll see labeled long data. This is the exact same data set we just created by summarizing our data. This data is long insofar as for each child, we have multiple observations for each year. We say it's long by child and year. What if we want to ask a research question that requires us to have simply children as the unit of analysis? Not the child year, but the child. Now we need each child occupying only one row in our data set. We can pivot our data, and I like to imagine kind of rotating the data on a diagonal, such that instead of multiple rows for each year, we now have one row corresponding to each unique child. And then instead of one column measuring our count of substantiated investigations, we have multiple columns measuring that same value in multiple years. This is a way of pivoting our data wide. And of course, as indicated by this arrow going in both directions, we can pivot our data wide, or we can take wide data and pivot it long. Pivoting is a key strategy in data manipulation, data management, so that we can make sure that our data are tidy. Lastly, and we'll talk a little bit about this at the end of our demonstration today, data cleaning can be pretty intensive. I've written scripts that clean data that can be multiple thousands of lines long. Often we'll find ourselves iterating different processes over and over again, and we may be tempted to copy and paste code. Copying and pasting code, though, can be dangerous for at least two reasons. One, it makes your code less interpretable. Second, it increases the risk of making unknown errors. Say I do something 6 times, and so I copy and paste it 6 times with slight alterations each time. Let's say I need to tweak something about that process, and I think I tweak it 6 times, but I only tweak it 5 times, or I forget that I need to tweak it multiple times at all. Copying and pasting increases the chances that I forget to make all of the adjustments I need. Programmatic coding makes repetitive processes more transparent and more malleable. We tell R explicitly to do something multiple times to apply some function or some process to multiple objects. The tidyverse is a very large package of functions that can help with programmatic coding. Base R includes other commands and functions that are helpful for programmatic coding. We can write our own functions, as we'll do a little bit later in the demonstration. And so this is a slightly more advanced topic, but I think a very important one, particularly if you're working with multiple years of data or a large number of variables that have similar properties. So now we'll start to pivot to our demonstration in R. And as we do, I just want to highlight a couple things about R. We're doing more demonstrations in R with the archive these days because R is an increasingly popular language in which to do analyses of archive data. It has the distinct merit of being open source, which means that it is free to you. If you want to work with R, I recommend that you use what's called a integrated development environment. In particular, I recommend RStudio, and I'll be doing our demonstration today in RStudio. This image here illustrates how you can download both R and RStudio and get up and running with R yourself. If you want to build on today's learning, here's a few additional resources that I very highly recommend. All of these resources, like R, are open source. And so if you search for any of these titles, you'll be able to access them completely free online. Okay, with that, I'll start transitioning to RStudio. And if you'll bear with me for a moment as I do that, I thank you. Okay, this is more or less what RStudio looks like. I'm going to give you a brief crash course in what you're looking at. In the upper left-hand quadrant is where you'll see your program file. Today we'll be working with a script which has the suffix .r. If you like to work in Markdown, that would also appear here as well. In the upper right-hand quadrant, you'll see the environment. R is essentially an object-based language. What we do in R is create objects and manipulate those objects. Any objects that R understands to exist will appear in your global environment. In the bottom left-hand quadrant, you'll see the console. Whenever R does things, it will tell you about what it's done in the console. The console is also a place where you can tell R to do things. I could type in 2 plus 2 here, hit enter, and R would do that math for me. But as I strongly recommended in my slide deck, I advise you never to code from the console. Instead, what we'll be doing is using our program file, highlighting different things we want R to do, and then hitting the run button in order to execute that function. Green text is anything that R understands to be a note or a comment or an annotation, so it's not something it will run. And I like to leave notes for myself at the top of any program file that I write. For example, these notes just say what this program file is, what it's for. Anyone who has any questions about this program file can contact me here. And then very importantly, I want to note to everyone in attendance here today that while the data we'll be using look very real, they are not. I've taken measures to anonymize the data we're working with today by partially fabricating them to prevent identification of the people that the data describe. So these are not real data, they're fabricated data. They'll have many of the same properties that real data have, so this should be a realistic presentation, but please understand this is not a presentation or analysis of NDACAN data. I also like to have a table of contents at the top of my program files. So I'll be walking you through some setup, a demonstration of some strategies for examining your data, for cleaning your data, and for coding programmatically. And then lastly, how to save your data in a way that will preserve the important work you've done. A brief reminder that if you feel we're moving pretty fast, don't worry. The code will be available to you on our website so you can follow through at your own pace on a later date. Okay, first thing to do is to set up our environment. As you'll see over here, R tells us the environment is empty, but if you've already been doing some work, it may not be. And so the very first thing I like to do in any program file is to clear the environment. Next, we'll load some packages. R has its own base language, a native language that it understands. But a lot of what contemporary researchers do using R involves user-written packages. You need to tell R to read in these packages. We're going to be using two packages today, data table and the tidyverse. Data table is very helpful for reading large files, and the tidyverse is a very, very large package with sort of an omnibus set of functions for data analysis. I like to use another package, pacman, to load other packages. The reason is that pacman knows if you've already installed packages or not. If you haven't installed them, it will go ahead and do it for you. If you've already installed them, it will go ahead and load it. The next thing we'll do is define some file paths. Basically just create some objects over here, which are just textual descriptions of places on my computer, locations on my computer. One of these locations is my project folder. The other is my data folder. You'll notice that the data folder is on a FedRAMP authorized cloud server. Lastly, we'll tell R that the project folder is our working directory. We'll set a seed, which is not relevant for today's demonstration, but will be in a couple weeks when we talk about missing data. And now we'll go ahead and read in some data. I'm going to read in 4 files, 4 years worth of NDACAN's child file data. Notice that these data are anonymized. They're not real data. Note also that I was able to do that pretty quickly, and you'll notice that each object, each sort of submission year has about 150,000 observations. That's because I've taken a very small sample of the whole NDACAN's child file. We'll only be talking about data from New England today, which is about roughly a very put it this way, a very small sample of the full data set. And furthermore, we'll be talking only about a small number of key variables. So I've already gone ahead and taken a sample of the actual administrative data just to make things simple today and also to make them computationally speedy. Distributed data files are very large, depending on whether you're working on a laptop or a desktop or on a server. Many of the operations we're doing today can take minutes or hours or even days when done on full data sets. So please be aware of this and plan accordingly. I often recommend that as you're troubleshooting and developing code to clean and manage data, that you work with a very small sample of the data, and then only once you've finalized your code, run it on the full archive datasets. We'll focus today on data from 2023, but as you'll see, when we start to code programmatically, we'll incorporate multiple years of data. Okay, let's first examine our data. As I said, most NDACAN data files are much too large to just open in Excel and kind of view by brute force in some sort of spreadsheet software. Even looking at a very small sample of the full NCAN's data, we see that there's 150,000 rows in this object. Excel very well may crash if you tried to open a file of this size. There are several helpful ways, though, to view snippets of the data in R. One way to do it is to tell R, okay, treat this object as a matrix, and then show me the first 5 rows and the first column of that matrix. What it shows me is the submission year variable and the first 5 values of that variable. We can get a little more fancy and say, okay, again, the first 5 rows, but now show me columns 1, 2, and 6. Now it shows us, again, the first 5 rows, but columns 1, 5, and 1, 2, and 6, which correspond to distinct variables. Very useful is the head function, which returns the first 5 rows of all of the columns in your data set. So we see here the first 5 rows for each variable in our data set. Sometimes, though, you may have more than 100 variables, and so head can be nicely combined with the select function. The select function pulls out columns by name that you want to see or work with. Now we're going to introduce something called the pipe operator. There's a sort of new pipe operator out there these days. It used to sort of look something like this. The pipe operator essentially takes the preceding element as the first input of the following function. It's kind of like saying, okay, and to whatever you've got, now do this thing. So take our NCAN's 2023 object, apply the head function to it, and then apply the select function to it, where we pull out these 3 variables. If we run this chunk of code, we get, again, first 5 rows and these distinct variables. Note that piping it in this way is equivalent to taking the data object, inserting it into the head function, and then inserting that into the select function. Identical output when we run it this way. In each of these examples, we're taking just the first few rows of the data. But sometimes it's helpful to get more of a sample of the data, even a random sample of the data. The slice sample function can be helpful here, where we take a 0.01% sample of the data set. And now instead of only getting records from Massachusetts, we get records from Connecticut, Maine, New Hampshire, and we get a greater variety of values for this report disposition variable. So slicing and sampling in this way can be a helpful way of examining your data as well. Okay, once we have started to get a sense of the structure of our data, we want to start cleaning it. Most data sets, as I've said, are quite large. And so before you invest a lot of time in cleaning them, it can be helpful to choose only those variables that you really plan on working with. You don't need to clean all of the variables in the dataset, only those that you really want to work with. I've already done this, of course, but just to make things explicit, let's create a new data set that includes only these variables. It's very important to understand that the data in the data sets that we distribute will not correspond exactly, the encodings in these data will not correspond to how they're described in the codebook. Overwhelmingly, they do. Universally, no. Let me give you a brief example. The count function counts up the number of observations with distinct values of a certain variable. The FC money variable is a variable that captures whether or not a child experiencing a maltreatment report was identified as having financial distress. What do we see? Well, 732 children in our sample had a value of 1, which means yes. 5,646 had a value of 2, which means no. And then an even larger number had a value of 9, which is what the codebook says is missing. But then as you'll see, the overwhelming majority of values have a value of NA. Nowhere in the NDACAN's codebook will it say that any values of this variable will have the value NA. NA is R's native way of encoding missing data. The codebook tells you all missing data will be encoded as a 9, but that's clearly not the case. So it's very important to verify how each variable is encoded. Note that this count function is actually just a special case of the summarize function, in which we group our data according to the values of a variable, and then count the number of rows in each group. In other words, the number of observations having each value. We could replicate this code by first grouping our data and then summarizing it to simply count the number of observations. As you can see, exact same table. For the reason I just demonstrated with the financial distress variable, it's very important to inspect the encoding or the values, the full distribution of values for every variable that you're interested in working with. Here's a chunk of code that I won't work through in detail. I'll just note that we use pivoting and counting in order to generate a table that shows us the number of observations having distinct values of each variable. Here again, we see the FC money variable has both values of 9 and NA. We have another variable in our data set, the relationship of the perpetrator to the child. We see that it's encoded in all of the ways the codebook suggests it should be, but a very large number of observations are also encoded as NA, which the codebook would not indicate. So for this reason, we need to recode our variables how we want them. As we recode our variables, it's pretty helpful to understand what kind of variables we're dealing with, what the format of each variable is. We can do this using the str function, which tells us, for example, that our submission year variable is an integer variable. Our 2-letter state identifier is a character variable. Notably, R intuitively understands that our report date variable is indeed a date variable having a certain format. Now we can set about recoding the variables of interest. Recoding usually involves the mutate function. We use the mutate function to create new variables or to update variables according to the properties of existing variables. So for example, let's recode our report disposition variable, where if that variable equals 99, we will recode it as NA. We will tell R that it is a missing value in the way R needs to understand it. Otherwise, or else, we'll leave it alone. Once we've done this, we'll further re-encode it, telling R that this is a factor variable, that it has certain levels, and that each of those levels actually has a substantive label, which we'll assign to each of those levels. We'll do the same for a variable describing whether a child has a prior investigation. Ditto financial distress. As you can see, we're adding information, adding detail to what R understands about each of these variables, and we're cleaning up or re-encoding missing data. Sometimes, though, we want to re-encode a variable in a completely different way. For example, the perpetrator relationship variable has a very large number of codes, and perhaps we're not interested in quite so much detail. Perhaps we don't care whether a foster parent is a relative or not. Perhaps we don't care whether a professional is a daycare provider or a group home worker. We can re-encode these multiple categories into a single category, professional or foster parent. Let's go ahead and run this large chunk of code and then examine the object that it creates. Again, just the first 5 rows of this new object. And you can see that our old perpetrator relationship variable has these numeric codes, which now in our new perpetrator variable have meaningful labels. Okay, so this is kind of encoding or recoding or cleaning by brute force. But as you saw, that chunk of code was pretty long and complex. Imagine that we were doing that over and over and over again over multiple years of NDACAN's data. Or imagine that we're recoding scores of variables for any given year. There's a lot of opportunity to make mistakes. So this is an opportunity for us to code programmatically in a way that will make things both more transparent and more reliable. I'm going to demonstrate 2 ways to code programmatically. The first is to recode multiple variables at the same time, which have similar encodings. For example, the variable chprior and fcmoney should both have an encoding where 1 is equal to yes, 2 is equal to no, and any other variable or any other value should be missing. And so what we tell R is to mutate across these 2 variables, where for any variable in this list, if it's equal to 9, we assign it NA. And then subsequently recode that variable or factorize it, where the 2 levels are recoded as yes and no. When we do this and compare it to the previous data set, we see that previously the fcmoney variable had both an encoding as 9 and NA. But after this recoding, we get yes, no, and NA only. Now let's try a second form of programmatic coding, where we'll recode multiple years of NDACAN's data at the same time. We've only been working with 2023 data. What if we want to clean 5 years of NDACAN's data at the same time? First, we'll make a list. A list is a kind of object that R understands, and this list will just be a list of the 5 different years of data. So we'll first create this list, and we'll see the list appear here in our environment. It's described as a large list having 5 elements. Each of those elements is just one of these data frames. An important thing to note, ideally, the names of variables would not change across multiple years of data. If we compare the names of variables in the 2021 and 2022 data, that appears to be the case. Same. However, if we compare the names of the data in the names of the variables in 2022 and 2023, not so. If we examine why, it seems to be the case that in different years, some variables are capitalized in different ways. So we'll need to deal with that whenever we're coding programmatically and manipulating or cleaning multiple years of data at the same time. Now that we've created a list of multiple years of data, we'll write our own function. We'll do this by creating a new object, which we'll tell R is a function. That function will have one input, which we'll call df for data frame. The function is then defined by everything that falls between these brackets. What's in the function? What is the function? Well, it looks a lot like that previous chunk of code, where we'll take an object, whatever the input to that function is, and we'll do a bunch of data cleaning. Notably first, though, we will rename any of the variables in any of those objects to all lower cases. This allows our variables to be the same across multiple years of data in which, in the distributed or raw files, they don't actually correspond. Then we'll recode all of the variables as we did before, because very happily, all those variables are consistent across multiple years. When we tell R to execute the code defining the function, all it really does is create a new object here, namely a function in the environment. The last thing to do is to apply or list apply the function to the list. We do that using the lapply function. This creates a new list over here, where the list includes not the raw data objects, but the new cleaned data objects. Of course, lists are a little bit counterintuitive and not the easiest way to do data analysis. So the last thing we can do is unlist the data, or essentially stack all of the elements in the list on top of one another to create a single data frame. We do this using the list rbind command, creating a new data set, NC corresponding to just the cleaned NCAN's data for 2020 all the way through 2024. And then if we take a small sample of that data, we see that it includes our new cleaned variables, but also data not only from multiple states, but also multiple years, 2023, 2021, 2020. This is a admittedly simple, but I think powerful example of how you can clean many years of administrative data reliably, transparently, efficiently. The last thing to do is to save our data. It's very common to work with CSV files. I do it very often. It's important to understand, though, that much of the encoding work we've done in R will be lost if we save it in a separated file. And so I often encourage people, as you're working with intermediate data files, to save using R's native data format, RDS, which will preserve the encoding that you've done. That's the end of my demonstration. Thanks for bearing with me. I'm going to pull up our slides once more and reiterate that we're here to field any questions you have about archive-involved projects. The user support line is the general support line, and folks who respond there will help triage and direct those inquiries to the appropriate staff. You'll see my contact and Elisa's contact information there as well. At this point, I'll stop talking and let Elisa manage the chat to support a Q&A for the remainder of the hour.
Thanks,
Everyone,
Alex.
for your attention.
Yeah, thank you, Alex, so much. This is a great presentation. We have time for a few questions. The first question that came in, can you explain further how a report that occurred in 2019 could end up in the 2018 fiscal year report?
Thanks. Great question. Yeah, it's a little more intuitive why a report occurring in, say, 2019 would end up in the 2020 submission year. Less intuitive why it would end up in the 2018 submission year. I don't have a good substantive explanation. It's a much less common scenario. I'm usually much more concerned about delays in reporting. It would show up in an earlier submission year, most likely if it was kind of right at the edge of the federal fiscal year. I think my top line advice here, though, is to be careful to think about submission year and data year as distinct frames. And so whatever your data year is, you need to think carefully, but also empirically about what submission years you need to adequately cover those data years. I suggested that as a rule of thumb, you should have an additional subsequent submission year. We're talking here about NCANs, really. An additional subsequent data submission year in order to cover each data year that you're interested in. But this can be verified empirically by downloading the data and looking at the timing of reports in each submission year. So the importance of this, the degree to which it will contribute to bias in your analysis, depends on the nature of your research question, the temporal sampling frame. I mean, mostly to highlight this as a potential concern and to encourage you to investigate it yourself using data empirically.
Great, thanks, Alex. The second question says, for those of us who don't use R, do you also provide these kinds of examples in other statistical programs, for example, SPSS? Just to answer that quickly, and Alex, feel free to add, we don't have videos which describe these data procedures in SPSS specifically, but if you send a message to the support email, which I put in the chat and I can put in the chat again, a data analyst who's familiar with SPSS may be able to assist you with any specific questions. And I don't know, Alex, if you have anything else to add.
Just a little. Yeah, it's tricky to serve a research community that uses a wide variety of statistical softwares. And we are candidly transitioning to providing a greater proportion of our trainings in R and R Studio. That said, when we distribute data sets, we often distribute code to help read in our data using the native data formats for different statistical softwares. So if you're an SPS user, not for all of our data sets, but for many of our data sets, you can read in a native SPSS format of our data. Some of our archived presentations have been done in other statistical software, mostly Stata. Some of those are no longer available on our website. But if you are, as Elisa said, looking for support with a specific software, someone on our team will be able to help you with that. And we may have resources that we can share on a case-by-case basis.
Great, thanks, Alex. And then just to address the two questions around if we're going to share the R demonstration codes, yes, I believe that is our plan. And Alex, if you want to share anything.
Yeah, please use it and adapt it. I really only learned to code by being given other people's code and adapting it to my purposes, studying it carefully to understand why they're doing what they're doing, how their code works. And so please don't hesitate to download the code, adapt it to your purposes, reach out with questions about it. That's entirely in the spirit of this presentation and the research support we do.
Yes, and then I saw that a third question came in about sharing the slides. Yes, we will be sharing the slides with the recording as well as the R code, and that will all be shared on the website. And an announcement of that will be sent on the listserv, which you can subscribe to. I put that link in the top of the chat. Thanks, everyone. I have a question. Do you use Tableau software for data analysis in trainings?
Short answer, no. But again, if you were curious about support in Tableau, I would email that main user support line, and we'll do our best to find someone who can support Tableau users.
And I saw that a participant raised their hand. If you could use the Q&A function to put any questions you have, that would be wonderful. Thank you. And if you need help finding that Q&A box, it's in the lower right of your Zoom screen. It has a question mark in a box. Thanks. I think we have time for one more question. And a reminder to, if any other more specific questions come up or questions come up after the call, like Alex said, feel free to reach out to our support email or to the emails that we put in the chat. And we're happy to assist with anything that comes up regarding this.
Yeah, and a brief plug for next week's presentation. We'll be talking about linking NCANs and AFCARs. That will build directly on much of what we talked about today. Some of the unit of analysis questions, summarizing and pivoting questions are especially useful when it comes to formatting administrative data sets for linkage.
All right, we're at the top of the hour, so just to respect everyone's time, we're going to go ahead and wrap it up for today. See you everyone next week, same time. Thank you so much, and thank you, Alex, for the presentation.
Thanks, everyone. Take care.
The National Data Archive on Child Abuse and Neglect is a joint project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. Funding for NDACAN is provided by the Children's Bureau, an office of the Administration for Children and Families.